in an RC circuit, then you would see an exponential decay. Other examples of exponential relaxation include damped oscillators and thermal relaxation of a body which is cooling or heating to its surrounding temperatures. But the thing is that not all the decays in the nature are governed by exponential laws. So the other examples might also include logarithmic relaxations, which are observed in certain cases, including current decay in superconductors, volume relaxation of crumpling papers, and so on. And other class of relaxation might also involve stretched exponential relaxations, as observed in decay of residual charge in glass Leyden jar, glass moving wells, and also in some astrophysical contexts where the stray bodies are removed from the solar system, following a decay law governed by the stretched exponential. So if you see these classes of relaxation, they are very slow. They may take a long time to reach to equilibrium. So these are anomalously slow relaxations. But in this talk, what I will talk about is another interesting class of relaxation, which are anomalously fast relaxation. And one best example from that category is Mpemba effect, which is related to the faster freezing of a hot sample of water than a cold sample of water when they are coupled to the same thermal bath. So, I mean, at first sight, this might seem that this thing is new, and definitely it's interesting because it has gained a lot of attention from the scientific community. But to argue with the fact that it's a new effect, I would say that its history actually dates back to Aristotle, 250 BC, when he realized the effect of the history of heating a sample on its freezing time. And thus he argued that people, when they wanted to cool hot water quickly, they generally begin by putting it in the sun. So after its birth with Aristotle, the effect grew up for several centuries with people like Roger Bacon, Giovanni Marlini, Francis Bacon, and so on, until it was accidentally observed by a Tanzanian teenager, Erasto Mpemba. So this was an accidental observation because once making he was taking part in the ice cream making competition in his high school. He was only in Form 6 at the time, and then he realized that by the time he would finish up making his ice cream mixture with milk and sugar, he would have lost the last available slot in the refrigerator, and therefore he decided not to cool down the mixture of milk and sugar, which he was supposed to do. Instead, he just put the hot milk inside the freezer, and then after an hour and a half, he and his friend went to look back at the situation of the ice cream. Then he realized that his hot mixture had turned into an ice cream faster, or was already turned into an ice cream, whereas the cold mixture, which was put in by his friend, was still in the semi-liquid phase. So that actually ignited the curiosity, like, why did this happen? Because I guess he was still a kid, but he was very inquisitive. So he kept thinking about that, and then he asked his physics teacher, like, why did that happen? To that, he was mocked by his fellow students and his physics teacher, which was very surprising. And his physics teacher said that all I can say is either you are mistaken, and if this is true, and if you insist that this is true, then I would say that this is Mpemba's physics and not universal physics. So having been ridiculed by his physics teacher, he didn't give up his hope, and he kept thinking about that. And because he believed on the primacy of the empirical evidences over the existing theories. So this time, he got another visitor from a nearby university, Dr. Osborne, who visited his school to give a lecture. And in the fear of being mocked by his students and teachers again, this time he put the same problem in a more scientific way. He said that, okay, if we have two containers with equal volumes of water, one at 35 degrees and other at 100 degrees, and put them into the refrigerator, the one at 100 degrees Celsius freezes first. Why? So I guess he was just playing smart by putting his own observation in a more scientific way. And this time, Dr. Osborne took him seriously, and he decided to verify his statement once he is back to his workplace. And when Dr. Osborne's lab members, they carried out the experiment, they actually found that Mpemba was indeed right, And then they published the first systematic study of this anomalous effect in water, where they showed that the time to freeze has actually a non-monotonic dependence on the initial temperature of the system. So this was the first ever of the experimental, systematic experimental observation of the Mpemba effect. Notice I'm still calling this an anomalous process because for a slowly cooling object, a system must pass through all intermediate temperatures. So the fact that you're starting from a hot temperature will only add an unavoidable delay in the cooling time, and therefore a hot object cannot cool faster than a warm object. Therefore, this effect has still been a paradox and it's unresolved. Part of the reason is that this effect is very tricky to reproduce, and the parameter time to start freezing, which basically defines this effect, is very ambiguous because this the freezing thing because of nucleation is a stochastic thing, and you cannot actually define that point. And one of the many challenges to observe Mapimba effect is that the systems where these effects have been predicted or have been observed are very complex, and they involve a number of mechanisms to explain the underlying mechanism, which included processes like evaporation, convection, supercooling, and so on. Although these effects, they have certain experimental evidences, or either independently or in conjugation with other effects, the actual underlying mechanism is still a topic of hot debate, and we still lack a consensus on the uh, exact role of these processes. Therefore, we take this as an opportunity to see if we can understand these effects. Therefore, we started to look in a colloidal system, and asked ourselves a question like whether we can observe these kinds of effects in a colloidal system. The reason were twofold. One is that first we can verify whether this is really this is a real physical phenomenon, and the second thing is to answer whether this is just specific to water and ice system only. So as the first step for our study, we started by putting up by the definition. So we say that the Mpemba effect would exist if the time to cool a hot system, TH, is less than the time to cool a warm system. Here we have our initial and final states, which are in thermal equilibrium with a heat bath. Notice we have an equilibrium initial and a final state, and these equilibrium states are very well defined. So there is no ambiguity in our definition, and this also removes the vagueness from the prior definitions of the Mpemba effect. And these times, TH and TW, are the time that the system spends between the initial and the final equilibrium states. So with this definition, the phase transition becomes an optional thing, because this definition would also hold for systems undergoing a phase transition, and also for a system that does not go through a phase transition. So after having a proper definition, we now look at our experimental setup. So we have a colloidal particle which is diffusing in a potential in water at the bath temperature, and the shape of the potential is a tilted double well potential, which has a metastable state and a stable state. And the overall potential is situated in a very small spatial domain, which is around 800 nanometers, which allows us to have a faster equilibration time of the particles in this potential, which will further allow us to do many repetitions of the experiment to create an ensemble state of the system at intermediate times as it relaxes to the equilibrium. Just one point to note here is we have an asymmetry in the left hand side and the right hand side of the potential, which means the size of the left hand domain and the size of the right hand domain, they're unequal, and that is characterized by a factor alpha, which we call as the asymmetry factor. We will look at the role of this factor after a while. But for now, since we want a potential like this, and people who do optical tweezers or people who manipulate potentials, they would know that these kinds of things are really tricky to generate with optical tweezers. So for this, we had to develop a special kind of technique to create such potentials. And the technique that we used is feedback trap. So a feedback trap includes mainly three steps. First is you observe the position of a particle using a detector or a camera, whatever you want, and then you calculate a force based on its position and also based on the potential that you want to impose. And then once you get that potential, when you get the force, you just have to apply that force. So the third process is the application of that force. It does not matter what is the source of this force. What matters is you need to be able to apply a force. And in our case, we used an optical trap to apply these kinds of forces. So basically, you can just shift a trap position, and that will apply a force following the Hooke's law, and then you can apply this calculated amount of force. In our case, we apply these forces at a bandwidth of 100 kilohertz, and the potential here, the black one, the potential that you form can be of any shape. You can create an arbitrary shape potential, which already overcomes the limit of conventional optical tweezers. And the potential that we form are generally called virtual potentials because they are not real, and these are discrete approximations of a real potential. So just to show what we can do with this experiment, basically I had to develop a setup based on optical tweezer and incorporating the feedback traps to create a versatile trap. And it took almost 3 years of my PhD time to come up with this setup, because the aim is not just to create a potential, but the aim is to create a potential to the accuracy of like zero point 0.1 kBt. So after developing this setup, we could actually do a lot of things. One of the example could include that we can actually create a virtual potential, which might be either weaker or stronger than the underlying optical tweezer. I mean, for an optical tweezer, for a given power, you have a fixed trap stiffness, and when you want to increase the stiffness, or even when you want to decrease the stiffness, you have to play with the power of the input laser. But here, what I showed is that you can have the same power, but you can apply feedback traps to create a much stronger or a much weaker trap. We After having played with this in like two dimensions, like x and y directions, we just played it with in three dimensions. And as you all know that for a standard Gaussian beam, the stiffness that you will have in x and y direction vary from the z direction. And because of the lower steepness of the laser beam, you will have a weaker trap in the z direction. So there, what we came up with is forming an isotropic trap where we have similar trap stiffness in all the directions, which basically gives you the same force bandwidth in three dimensions, and then you can avoid calibrating the system in different directions independently. And that will basically ease up your life for doing a 3D animation of the object. As I said earlier, that we can actually create arbitrary shapes of a potential. We could actually show that we can create a double well potentials, we can create a V-shape potential, and of course the harmonic potential that we just talked about. And if you notice at the length scale of these potentials, you will see that these length scale are way below the diffraction limit of our system. I mean, for this particular case, I can say that the diffraction limit was around 300 nanometers in our setup, but the features that we have are way below those length limits. So in order to check how far we can push these limits, we just created a potential where the wells are separated by only 10 nanometers, which is very, very exciting because you can create such kinds of potentials with optical tweezers at these length scales, but still keeping the curvature pretty high so that you can have a two-state system in your experiments. So these are just for other applications of the feedback trap that I developed in my PhD. But the aim is still to go back to the previous thing and just see whether we can create the potential that we talked about for the Mpemba effect. And actually, we could create a tilted double well potential that I just talked about. And the small length scales here will facilitate faster dynamics, which will allow us to repeat the experiment many number of times. So having set the definition and having been able to create the potential that we want to use to explore the Mpemba effect, now I will outline the quenching protocol. So in our quenching protocol, we prepare systems at different initial temperatures. So these are examples of the Boltzmann distribution at different temperatures. So here TB is the bath temperature to which we will cool down our system. And the idea is to just pick up a point, like just you randomly sample a point from the Boltzmann distribution and release your particle there. So on this left hand side you have a red trace that corresponds to the Boltzmann distribution at a very high temperature, which we call as the hot state here. So you sample a point, a position from here, and then you take your particle there and release it until it reaches the thermal equilibrium. And then you repeat this process many times. So here, this is just an example with 10 traces, but actually we do like 1,000 runs to carry out this experiment. And then once you watch the system evolve from the initial temperature and to the final temperature, then you can create an ensemble estimate of the states of the system at any instant of time. So a naive observation or a naive guess that you can say is that, okay, once we have a system cooling from an initial to the final temperature, then it's pretty easy that you just measure the temperature and then you will know how the system is relaxing to thermal equilibrium. But then I would say, wait a minute, that since this is a quenching process, so the system, when it is released from an initial point or initial state, is no longer in thermal equilibrium, and temperature is a quantity that you define for a system in equilibrium. So there is no point in finding a non-existent quantity in this system, because at intermediate times the distribution might be in such a way that they won't be characterized as temperature and will not lead to a Boltzmann distribution at a particular temperature. Therefore, we need a distance measure to estimate how far is an instantaneous state of the system from the equilibrium states. To this point, Liu and Rods, they just came up with a certain set of criteria where they say that a distance function can only be used as a proxy of a temperature if it follows certain properties. So here they argue that if a distance function is a non-increasing function of time, which means the distance when the system starts to relax should only decrease, then it would serve as a proxy of temperature, and it should be a monotonically increasing function of initial temperature. Like the farther you go from the bath temperature, the distance function should keep on increasing monotonically. And third one is it should be continuous and convex function of probability. So this one is very tricky, and it is actually used in the derivation of the expressions to prove that the distance function can be a proxy of temperature. So these two are physically realizable here. And in our case, we used an L1 distance function, which is just measured as the absolute difference of the instantaneous probability pi and the Boltzmann distribution pi I. So this is a very simple distance function, but it doesn't mean that this is the only one. Like any distance function, for example, the Kullback-Leibler or the entropic distance, which also follow these criteria, are also like good candidates to be used as a proxy of temperature. But we will stick here with the L1 distance. Part of the reason is that this is a very easy thing to calculate. And the second one is that it also eased our calculation to analyze our experimental data. So having said this, now we will look at some experimental data. So this one you have seen already. So what I wanted to show you here is that since these distance functions are measured from the probability densities of the system at each instant of time, so what we can do is that we can calculate similarly the distance function d as a function of time from these states that you can find at any point of time. And then you can see that this is a non-monotonically increasing function, and the system starts a certain distance and then it reaches to the bath temperature. So I will come to this point after a while, that why is this the bath temperature? Why doesn't it go to zero? But I will throw that to you guys to just think like why it doesn't go to zero. But for now, we can also carry out a similar analysis for a warm system. That here I have a warm system starting at a temperature which is very low than compared to the hot system. And a naive guess would say that, okay, since this is a warm system, the d function should start from somewhere here. It should be definitely lower than the hot system, and then it would reach the equilibrium faster. But to our surprise, it does start from a lower value of D, but it lags behind and it takes a lot of time to reach to the thermal equilibrium. And the crossing between the hot system and the warm system tells us that the Mpemba effect actually exists, because high temperature, a large value of D goes to the bath at a rate faster than the warm system, which started with a lower value of D. And we also did a control experiment where we prepare our initial system at the bath temperature and then we release it into the same bath. So you should ideally observe that it is not going anywhere. And it is indeed true that we see a constant level of this D function corresponding to the bath temperature. And that's why I said that this level corresponds to the bath temperature. So once you have this, then you can use the time, then you can calculate the time at which these systems reach the equilibrium. So for example, the hot system reaches at this time TH and this one is TW. And now we can see the effect of the temperature, the initial temperature of the system on these equilibration times. So we first consider one particular case where we have alpha equal to 1. Remember, this alpha was the ratio of the right-hand side of the domain to the left-hand side of the domain. And for alpha equal to 1 means we have the symmetric geometrical sizes of the potential on the left and the right side. And in this case, we observed that the equilibration time initially increases with the temperature of the system, but after a while at high temperature, it saturates. So basically, this is just a scenario of a normal cooling that we generally see. Now, if we introduce a small asymmetry in this potential by making the right-hand side 3 times than the left-hand side of the potential, then we observe that initially the time to reach to the equilibrium increases with the initial temperature, but after certain temperature, here around 10 TB or 10 T naught, the system starts to take a smaller amount of time as the initial temperature starts to increase. And this is indeed a graph similar to the Mpemba's observation, where he saw that this thing has a non-monotonic behavior with the initial temperature. So I mean, inspired us to introduce a bit more asymmetry into the system. So we now make the right hand side 9 times bigger than the left hand side of the potential. And in this case, we observe that up to T naught equal to 100, the equilibration time has the same characteristic behavior as we had in alpha equal to 3 case. And after this, we see that the equilibration time again increases with the initial temperature of the system, which is generally the expectation for a system undergoing normal cooling. So in this case, just if I have to summarize these 3 plots, then I would say that the region of the temperature over which we have a negative slope will correspond to the region where we can have the Mpemba effect observed. So in this particular case, we see a sequence of normal, anomalous, and normal cooling. So we can see a whole sequence in this particular case. And just to see what's happening in the background, we can look at the distance functions, which we just talked about earlier, but only for one particular case. But now we have for different cases here. So the red traces are the systems relaxing to the thermal equilibrium at different initial temperatures. So if you closely look at these distance plots, then you will see that these relaxation curves, they have 2 kinds of time scale. One is a time scale, which is the fast time scale that is basically driven by the kinetics of the system. And the second time scale corresponds to the barrier hopping between the 2 wells. Remember, we had a metastable and stable states. So the particle keeps hopping between the metastable and the stable states, and this is determined by the Cramer's hopping rate. And and this is present in all the data. But if you look at this particular case, T naught equal to 100, then you would observe that the slow time scale, which was present in all other situations, is actually absent in this one. And that's why we say that this one is the fastest cooling temperature among other plots here, and that's why we had a dip in the equilibration time. So this was part of the reason that one of the time scales, the slow time scale, which will ultimately govern the cooling time of a system, is absent, and that's why it took a less amount of time. Just to explain this point a little bit in a different context, so that you can have a physical picture in mind, we can do another kind of experiment where we fix the hot and the warm temperatures. Like we have a fixed hot temperature and a fixed warm temperature, and this time instead of varying the temperature, we vary the asymmetry parameter. Like we go from a very symmetric potential to a very asymmetric potential. And again, in this case, for alpha equal to 3 case, you can see that the slow time scale, which is present in all the other graphs, is actually absent in this one. And to understand this one, we can look at this cartoon. So imagine that you prepare your system initially in such a way that the total population of the system in the right well and the left well of the potential are exactly same as, or approximately same as, the corresponding potential at the bath temperature. Then this probability, which is just right case here, relaxes into this local well, and this probability relaxes into this local well. And since they're already there in terms of the total population, so it just relaxes locally in those wells, and it avoids any hopping between the potentials, between the barriers. And that's why it takes a very small amount of time. And remember, I also told you that this slow time scale corresponds to Cramer's hopping. So if you don't have those hoppings, that means this time scale is going to be absent. And that's why for this particular case, this was absent. But if you have too much probability, for example, in alpha equal to 9 case, then once you relax locally to the well, then you have a lot of probability, and then you will have to hop over the barrier to reach the final equilibrium, and that's why it will have an uh, extra time scale, which is a slow time scale. And the same thing will happen for too little probability. For example, for alpha equal to 1 case, where you had so much that most of the probability went to the left hand side, and therefore you have to hop from the other side to reach the thermal equilibrium. So in this case, too little and too much, you can have the slow time scale. And if you are just there, then you don't have the slower time scale, and then you reach to the equilibrium faster. And we will see in a bit that actually these processes are exponentially faster. And why I say that? The reason for that would come from a quantitative analysis. So far we have a qualitative picture of the thing happening in the background. So now, to do a quantitative analysis, we just use a Fokker-Planck equation, which governs the evolution of a system to probability densities. The probability density of the system at any time t and any position x can be given as an infinite sum of the eigenfunctions of the Fokker-Planck operator L here, where the contribution of all the modes, they decrease with they decrease exponentially with e to the power minus lambda kt, where lambdas are the eigenvalues of this Fokker-Planck operator. And if you approximate this potential in the long time limit, then you would just have only two terms. One is pi of x and tb, which is the Boltzmann distribution corresponding to the bath temperature, where the system would eventually go in the infinite time limit. And we are left with only one time scale here, governed by e to the power minus lambda 2t, which contains the second eigenfunction of this potential. And since this is the slowest time scale, that's why we can ignore all other time scales which are faster, because if you have many modes, then the slowest mode will be the determining factor. So that's why we have only this one here. And actually, Liu and Rods, they said that the amplitude of these potentials, sorry, amplitude of these eigenfunctions A2, they have a very determining role in observing the Mpemba effect. They said that, uh, I mean, they laid out a certain rule for this A2, which we will just talk in a bit. But for now, what we can learn from this is that theoretically, this A2 can determine whether the Mpemba effect can be observed in a system or not. But this A2 is a numerical thing, and it can also change signs because it is just an overlap between the second eigenfunction and your initial distribution. So these numerical things can flip signs. And actually, what we did in our analysis is that we used distance functions, which are strictly non-negative. So with only a positive quantity, you cannot calculate a quantity that can change signs. Therefore, we came up with another way of doing it. So what we did is that we extrapolated the small time scale, the small time regime of this decay curve back to t equal to 0, and then we took this difference, which is the extrapolated value, and subtracted the noise flow from there, and calculated the quantity delta d, which is indeed proportional to the absolute value of this A2 coefficients. So not just A2, it's the absolute value of A2 coefficients. So this thing is pretty easy to calculate from our distance functions, and we actually carried out this, and then we found that for alpha equal to 9 case, this delta D has a non-monotonic temperature dependence. And and when we did the same calculation for our other sets of measurements where we fix the temperatures and change the asymmetry factors, we again see a non-monotonicity in the variation of this delta D. And for all the cases where we have a delta D value at a hot temperature less than the delta D value at a warm temperature, we would see the Mpemba effect, which strictly goes with the Oren's prediction that Mpemba effect would exist if the absolute value of A2 at a hot temperature is less than the absolute value of A2 at a warm temperature, which goes in our language in terms of delta D. So it just replaced this A2 with delta D. So for the temperature range here, where the delta D values are smaller than the temperature values, let's say here, then we would observe the Mpemba effect. This kind of intuition we had already from our equilibration time curves. Since we are looking at the role of this A2 and delta D, so which is given by the slow time limit of this equation here. But if you look at these two particular points where we see that they are approximately equal to 0, which will cancel this term, like this will remove the role of the second eigenfunction, and therefore the dynamics of the system is now governed by the next higher order term, which is governed by e to the power minus lambda 3t, which is exponentially faster than the rate controlled by this term. And that's why these conditions where the delta D values are approximately equal to 0 corresponds to strong Mpemba effect, which is the exponentially faster relaxation of the system as compared to other systems starting at non-negative value of delta D values. And this was the first experimental observation that we did in our colloidal system, and I guess so far the only one available out there. So I mean, having developed the picture of this Mpemba effect in terms of equilibration time and then delta D values, and a simple question that you may ask is that, okay, well, you understand this effect so much, then can you predict the inverse of this effect? Like, do we believe that the converse, like when you start from a cold system and a warm system and then you heat it up, does it happen that the cold system takes a small amount of time to become hot? So to answer that question, I would partially say that, okay, this thing is actually predicted in Ising antiferromagnets. It's been predicted only. There is no experimental evidence. And later on, this effect was also predicted in other systems, for example, spin glasses and granular systems. So this motivated us to consider this effect in our case, like in our colloidal system. And actually, when we performed a heating quench, which is preparing a system at a cold temperature and then quench it to a heat bath, which is hotter than your initial preparations, then can you observe this effect? And actually, we did. So we just followed the similar kind of things that we did for cooling experiment here for the heating one. And the way to read this graph is from here, that when you are close to the bath temperature, which is when T naught is equal to TB, when you're at 1, then the system takes the least amount of time because it is already there. And as you deviate from the bath temperature, it starts to take more and more time to reach to the hot bath, but only a certain temperature. And after which you see that the colder preparations actually takes less amount of time to heat up. And this is the anomalous behavior in this heating trend. And then after a certain point, we see that it starts to follow the normal heating behavior. So again, we could see a normal to anomalous to normal heating behavior. And based on our distance functions for this inverse effect, we could also come up with delta V functions, which now you have an idea that this would also be non-monotonic. And in this case, we also saw the strong inverse Mpemba effect. So for the results of this strong Mpemba effect and the inverse effect, so far this is the only experimental evidence that we have. I mean, in any kind of system. So we are glad that we could see this effect in colloidal systems. So now if you take a step back and look at the Mpemba effect and the inverse Mpemba effect, then one common thing that you can figure out from these experiments is that they had certain kind of asymmetry in their potential. Either they had an asymmetry in the domain sizes, or they had asymmetry in the energies of the wells, or actually it was present. I mean, both of them were present in our cases. So then the question that you can ask is, are they really important to see the Mpemba and the inverse Mpemba effect? Like, do we really need the system to be asymmetric? So that was a very tricky question, and I got a small amount of time towards when I was writing my thesis to think about that problem. And then we decided, okay, let's start to remove these sources of asymmetry. So before that, let me remind you that we had actually done one part of the experiment earlier when we had alpha equal to 1 case, where we had removed the geometric asymmetry in our system. And in that case, we had observed that the equilibration time was not non-monotonic. So it was a normal cooling behavior. So no Mpemba effect was observed. So now there is only one source of asymmetry, which is the difference in the energy of the wells. So we came up with an experiment where we thought, okay, that we can make these potential wells symmetric. Like there's no difference between the energies of the well. And to our surprise, I found that we can actually find the Mpemba effect in this case also. Remember, the crossing between the D curves of systems at two different temperatures will indicate the Mpemba effect. And here, the hot system and the warm system, we see, I mean, for these systems, we see a crossing between them, and that indicates the Mpemba effect. And we had to do a much more number of repetitions as compared to our forward Mpemba effect one, where we just did 1,000 repetitions. Here we are doing like 30,000 repetitions to see clearly the crossing between the two curves here. And to just to confirm our experimental finding with the numerical predictions based on Fokker-Planck equation, we calculated the A2 coefficients and A3 coefficients. I will tell you why we calculate A3, because A2 coefficients are zero here because of the symmetry reasons. So the dynamics is now governed by A3, and therefore the role that A2 was playing when it was the key player will be played by this A3 coefficients now. So if there is any non-monotonicity in this A3, then we would see that, okay, that is going to govern the Mpemba effect in this symmetric potential. And we do see that we have a non-monotonic dependence of this coefficient. And that's why, I mean, we call this as a higher order Mpemba effect. This effect has not been predicted earlier, so we predicted this, and we found that this is actually possible to be observed in an experiment. And if you just think a little more, then you will realize that a while ago I told you that A2 coefficients corresponds to hoppings between the barrier. And now I'm saying that this A2 coefficient is zero. It means there is no hopping between these barriers. So now one can ask, like, do we really need these two potential wells, or is just one well enough? So to answer that question, we can just truncate our potential in the middle, where we have only one well. And notice we don't have any symmetry here. So the A2 coefficients will come back again, because I mean, nominally it won't be equal to zero because there's no symmetry. And now we can look at this behavior of A2 as a function of initial temperature, and then we see that still this guy has a non-monotonic temperature dependence. It means it should be possible to to observe the Mpemba effect in this kind of potential. So this is just so this particular slide is just a numerical prediction that I came up with, but I didn't get enough time to work on this because at some point I had to stop doing my PhD work and move on. So I guess this is just a problem to another student in John's lab to see whether this thing is actually observable in experiments or not. So with this, I would like to summarize by saying that we saw the Mpemba and the inverse Mpemba cases in quenching cases where we quench the system to a hot or a cold bath, and these are strongly non-equilibrium processes. So if you think of these processes through the lens of Newton's law of cooling, then I guess you are doing the wrong thing. You are having the wrong guy to catch the wrong thing. And the second thing is that we observed experimentally the Mpemba and the inverse Mpemba case, and we also found the strong versions of both the cases. And actually, the strong versions of the inverse Mpemba and the inverse Mpemba itself. This is pretty new, and we have submitted this work uh, to PRL, and this is an archive, and we're just going through certain revisions, but it will appear soon for you guys to read up. And and if and the observations that we did for the inverse and the strong and the forward Mpemba cases were done in potentials which were asymmetric, and those asymmetric potentials actually serves as a very nice model for the ice and water system. Like the metastable state can actually serve as a supercooled liquid, and then the stable state can serve as the cold liquid. So the asymmetry in the potential was a TWI model for the water and ice transition. But our observations in the higher Mpemba case, where we showed that we don't need actually this tilt in the potential, which takes the effect further away from phase transitions. And therefore, I also talked in the beginning that this Mpemba effect is not specific to water where we have phase transitions. We can actually observe these effects in systems where we don't have those kinds of phase transitions. Huh. And as an outlook to this work, what I can say is that we did our experiment and we showed the Mpemba effects, both the forward and the inverse effects, in a setup which is a very clean setup, and I guess we know a lot about those setups and what is the dynamics of the particle in those kinds of potentials and so on. And our agreement and our results from our experimental data, they were in very good agreement with the predictive theory based on the Fokker-Planck equation, which can also be applied in many other systems. And based on our intuition from this system, we can now take a step further to understand what's happening in more complicated systems. And actually, people have tried to see these kinds of behavior in other physical systems, for example, antiferromagnets, polymers, nanotube resonators, granular fluids, spin glasses, and so on. So in this talk, we just reserved ourselves to talk about only the one kind of anomalous behavior, which was the Mpemba and the inverse Mpemba effects. But in nature, there are other anomalous relaxation processes. For example, the Leidenfrost effect, which is related to the non-monotonous survival time of the liquid droplets when you put them on a hot plate, and the Kuvax effect, which takes the system away from the equilibrium, which was actually induced because of an external force. But when you remove the external force, then the system still continue to be in a state of non-equilibrium. So it might be very interesting to see whether these kinds of effects can also be observed in other kinds of systems. So finally, I would just like to leave you with my summary slide by just adding now one more point that although in the beginning I started to talk about Mpemba effects in water and ice system processes which govern those things, but eventually I plunged into giving you my results in the colloidal system, which you can say by giving some logic that this is not exactly the one to explain the Mpemba effect in water for the ice and water system. But what we can see here is that the analysis or the kind of things that we did in our experiment based on the probability flow of the system is actually analogous to the temperature field in bulk water. They both, I mean, both the quantities, they have a similar mathematical structures. For example, this probability flow is governed by the Fokker-Planck equation. The temperature field is governed by the heat diffusion, and in certain ways, they have similar kinds of structures. They have the similar kinds of solutions. They both involve infinite sums of eigenvalues. They have their solutions are all linear. So that's why we can say that the intuition that we get from this system might be applicable to systems which are bulk, like bulk water system. And hopefully, we see, we wish that after a certain while, this debate would be over. People would come up with the exact mechanism behind this effect. But I strongly believe, and it's my personal opinion, no offense, that I think if there is, if there comes, if we all come to a common cause for this effect, I think the reason would definitely involve the point of view that I did in my PhD work in the colloidal systems. So that's all for me. So I'll be open to questions and suggestions. Thank you for listening to me patiently.
Yeah, thanks, Dr. Kumar, for enlightening talk. So, any questions from the audience?
Yeah. Hi. Hi, means, so this is Anand. So I'm audible or something?
Yeah,
Yeah. So you said in the starting that means this reproduction of this Mpemba effect is unambiguous, right? Agreed?
yeah.
Okay.
Is
So,
ambiguous.
the parameters are unambiguous.
Unambiguous. No, I okay. Maybe I slipped. I said the parameters that people generally use, like the time to start freezing, is ambiguous.
Okay. So, okay. It's, I think I heard it wrong. Okay. So,
Maybe I just slipped.
okay. And what do you mean by virtual potential when you say you can actually measure that potential? Still, you are saying virtual. Why?
Oh, the reason we call it, okay. So a real potential is a potential that is actually present, right? So you have a potential, and then you
Okay.
can create forces out of this. Imagine a trap. So you have a laser beam, and then you
Yes.
have a potential, and then the particle would feel a force from that potential. But in a feedback trap, what we do is that the potential that we are creating is not actually there, right? We have only a harmonic well, and then we just bounce this harmonic well back and forth between using a defined rule to create a potential, so which is not present there. So this time we are using a force field to create a potential. Is that
Oh,
clear?
okay. Oh, okay. So, means that means the potential that you are creating will have some force. Agreed. Means if we will
Yes,
take the yeah, okay, gradient or something, then there has to be some force come out. Huh?
yes, yes.
And that force means when you say it's a virtual, what is that means? It's complex or imaginary or what? I mean, I'm not getting that
Virtual
point.
means it's imaginary, you can say. So let's say that
Okay.
we have a double well potential here, but we want to create this potential. What we have is this blue dashed line. We have a harmonic potential. So now
Okay.
imagine that if this thing was real, the black one was real, and if the particle is here, then the force that you will have is just the negative of the derivative at this point, right? Do you agree with me?
Yeah. Yes.
Now, if I tell you that this potential is not present, but you manage to give this particle exactly that amount of force, then you can imagine that there is a potential, but actually there is not. So the force that you're applying is from this harmonic well, which was not this double well that you want to create. So that's why I'm
Okay.
saying that the forces are not coming from the physical potential. We are creating a complex force field, and once you map out the particle, the movement of the particle in that complex force field, and then you estimate the histogram, and then from there you calculate the potential, you would come up with as if the potential was actually there. And part of the reason that I'm calling it virtual, because in a real potential, as soon as the particle position changes, the force would also change. But in a virtual potential, this is not going to be the case, because this comprises of three steps, right? So the two steps are just getting the information and calculating the force, and in the third step you apply the force. And I have a force, I have a loop bandwidth of 100 kilohertz. That means I don't update the force for 10 microseconds, which won't be true in a real potential, because as soon as you change the position, it will change. So in those cases, I say that these are virtual potentials and these are discrete approximations.
Okay. Yeah. Thanks.
Yeah.
Hi Avinash, how are you?
I'm good. Hi, sir.
Good, yeah. It feels so proud to see somebody from this lab do such fantastic work.
I guess everyone is doing pretty well.
Very nice work.
Yeah.
Very good. So, yeah, I heard the thing. Today has been pretty stressful. We had a lot of talking and all. Anyway, so just two things I wanted to know.
Yeah.
One is you're talking of these, this is so this whole problem can, I think it can be cast in terms of probability currents, as you said, right?
Yes.
So can we look at this as, can we sort of approach this in terms of how the entropy in the system sort of evolves, total entropy produced in different conditions, and how these can be sort of, I mean, so do you think that entropy can also be a signature of the Mpemba effect?
I guess you're right. I mean, you're actually pointing to the correct thing here. Definitely, entropy drives these phenomena, and I guess I should go to the end slide here, where I just showed the potential for the Mpemba effect to have a finite amount of energy barrier, like it was around 2 kBt, and for the inverse effect, it was negligible. It was like 0.002 kBt. So that was very small. And in that case, we can say that since the energy landscape is almost flat, so for the
Mhm.
inverse Mpemba case, the whole process was just driven by entropy.
By what? Sorry.
By entropy.
Okay.
Yeah. So actually, you can look at all of these things through just entropy ways. I mean, I
Exactly.
guess this is
Good, good.
totally feasible thing.
So yeah, I was asking because we have this method of, quantifying entropy. So these can be interesting problems to look at this way. Good. Acha, second question is closer to my heart, and that is something which was your baby. So you were the guy who developed the photophoretic thing in our lab,
Yes.
right? So
Yeah.
what do you think about Mapamba in the photophoretic trap? Because there we actually give, it's all real temperatures. We actually can heat, cool, do whatever we want. Do you think there can be some possibility of seeing manifestations of the Mapamba effect in photophoretic traps? And especially now, we do a lot of nice trapping with multi-mode fibers, so they give you a very, very interesting potential landscape.
Yeah.
Okay, so you can,
I guess
so
it should be
can you
totally
think of this? I
possible.
think we can do some pretty interesting work then, because we have this thing working, and this would be different because that would be in air, and we are actually heating them, and also like one, I don't know. I mean, you can look at possibilities of we are measuring Brownian motion as well. You, in fact, your paper was on that, right? And we are probably re-establish the capability of again measuring Brownian motion. So, do you think that one can sort of see these things? I don't know. I mean, just this is wild, just
Uh,
plucking from the air. What
I
is your
guess
feeling?
I guess it should be feasible. I mean, there is no reason that it should not be observed in those systems. But I guess certain modifications in the setup will have to be done. For example, I mean, as I said, like just to easily observe the Mpemba effects, the potentials were asymmetric, right? And I
Mhm.
guess if there is a way that you can use your AOM or just you modulate your laser beam with AOM to come up with the kind of potentials that I just showed here. And I guess it's pretty simple, right? Applying a feedback
Yeah, yeah,
frequency,
that is, yeah.
it's very
Yeah.
simple. So once you have that, um, and okay, so when you said that you can change the temperature, so
Mhm.
you mean just by changing the laser intensity, right?
Yeah. I mean, because that that is how the thing works, right? Because
Yeah.
change the power, it gets hotter and colder, and it moves up and down and all. And because now we have this multimode fiber, potential, which is, we have seen it's like extremely robust. The straps are very, very robust, and they actually have these particles in multimode traps. Sorry, they actually have some kind of a trajectory of their own. They're not stable. They don't not at rest. So that you guys also showed that you actually have that secular frequency and all. I mean that rotational frequency, right? So
Yeah.
I don't know. I mean, those might be manifestations of. I don't know. I mean, you can probably take, but that asymmetric thing, I don't know. That see, I do not think that the potentials are symmetric here in any way, because these are very dirty potentials. Only thing is whether you can control them. That I don't know. I mean, maybe one can just try to visualize the potentials and see how symmetric, asymmetric they are. And then I don't know, maybe one can just do an experiment where one goes from low power to high power, and the other one where they come back from high and low, and then see if the whatever the trajectories are the same or something like that. I don't know. It's a very naive thoughts that I'm having, but maybe you can think on these things.
Yeah, I guess that's totally feasible. I mean, all you have to, I mean, you can imagine a multidimensional space, for example, where you have many local minimas, for example,
Exactly.
and imagine a
Exactly.
scenario where when you start from a very hot temperature, then while the system is going to the cold temperature, then it gets trapped into some local, some metastable states, and therefore it takes a long time. Whereas in some cases it may happen. Sorry, I just said wrong. So if you have a warm system, and then you go to a cold one, then you may get trapped in some metastable states, but you can find a similar way where when it starts from a hot system, it takes another path and then avoids that metastable state and goes to the global equilibrium. So that's a scenario for this multidimensional case. Um, but I guess
Maybe you
if
can
you have
spend some
many,
time. You can even talk to the people who are working now.
Mhm.
Sovik is there. You remember Sovik? I think was with you, right?
Yeah,
Sovik Seal.
of course
He's
I know
sort of going
that.
to get out. Yeah, you maybe just have vague recollections. You probably just spent few months.
Mhm.
But he took over the experiment from you, and he's almost at the end of his road. But he's, I don't know, maybe one can connect. You can just think of what one can do.
Yeah, I would be happy to discuss this because that one is pretty close to my heart. So photovoltaic thing and all.
Exactly. That was you who built it, man.
Yeah.
Okay, I'll stop because I'm having a lot of issues in coughing. Okay,
Oh,
but
okay. Take
okay,
care.
yeah, yeah,
It was nice talking to you, sir.
yeah, yeah. I just joined because you were giving the talk.
Thank
Okay,
you.
Avinash,
Yeah,
take care. You're in Canada. Where are you now?
I'm in US now.
Huh?
I'm in US.
US, no?
I
Yeah,
joined
yeah. Okay.
here in the biophysics department here.
Okay. So do connect when you're here. Do visit the lab. Hopefully, it will be in happier times, not like this.
Yeah, I
Okay.
think so. I mean, I'm just finding
Mm.
a way to go to India because it's been like 3 years.
No,
I
no,
haven't.
don't even try coming now. It's horrible.
Yeah,
By the way, your family is safe here.
yeah, they are safe. Hopefully.
Okay. Chalo, Avinash. Good. I'm leaving
Okay.
now because stay. But I'll ask Sovik to connect with you. Maybe Anita is
Yeah,
also there.
we were
Just
just
connect.
chatting before this session today. So yeah, I'll definitely talk to him.
Okay. Very good. ठीक है
Okay.
यार. Goodbye.
Yeah. Thanks, sir. Bye.
Avinash, I have a question.
Yeah, sure.
This cold atom physics, when you go from microkelvin to nano, do you think this kind of physics may apply there or might be working there already?
Uh, I think this can be applied. I mean, I don't think there is anything stopping this effect to be observed because the kind of things that we have done are quite general, right? Like these kinds of things you can have in all cases. So there is nothing specific in this system. So if you want to see this in cold atoms, I mean, I haven't seen or I haven't heard of anyone doing experiments in that, but I guess this should be
Yeah,
totally
I
possible.
think this is possible. I think it's a good idea. I like your talk. Very nice talk. Good work. Yeah.
Yeah. The only thing that I don't know yet is like whether this system can be observed in biological systems. So
Hmm.
that's the thing. I mean I've been trying to think for a year now that what are the conditions over which we can see this effect in biology, like some protein foldings or all, but
Hmm. Hmm.
I haven't been successful in that.
Hmm. Okay.
Yeah. Yeah. Any other questions?
Any question? Okay, so there is no question. I think I thank you again, and I just need to show you a token of appreciation. So I will present that. I think it's visible, right? Yeah.
Not visible, Visajit.
Oh, it's not visible. Okay.
Yeah, I can only see you.
Now?
Yes, got it.
Yes.
Yeah.
Okay. Yeah, that's actually
Yeah.
great.
Thanks. Yeah.
Yeah, it
Okay.
was very nice to talk to people in IISER, because I mean it may happen that I don't know most of them, but IISER is still there. So that's the connection.